So our next speaker is Nabin Kalauni.
Hello, everyone. I'm Nabin. I'm at the University of Arizona in the Hydrology department. I'm a second year master's student. I'm working with Andrew Bennett, and I'm presenting a hybrid differentiable model for predicting land surface fluxes. So, before I get into it, first question is why do we need to model land surface fluxes, specifically the sensible and latent heat fluxes? And the reason for that, there's multiple effects, especially on downwind precip and on management for agriculture and water resources. But the main point is that our climate models will be biased if we're not doing our flux partitioning correctly. So it's important that we get this correct. And next, I want to set the stage for why we need machine learning in land surface models. So specifically, this paper, Best et al. Showed that even simple three-variable linear regression can outperform complicated land surface models, especially for sensible and latent heat fluxes. As you can kind of see from the graph over there, the one on the bottom is a three-variable linear regression model, and it does better than all the land surface models above it. So this shows to us that the current physical parameterizations that we have in our land surface models are wasting information that's in the forcing dataset. So this presents, I think, an opportunity to use neural networks to try and uncover what we're missing from our physics parameterizations. And the next point I kind of want to touch on is this age-old problem of numerical demons in hydrology. So as you can kind of see from the top left figure, the explicit Euler way of solving our models can lead to a loss landscape that's extremely jagged and can lead to a wildly different outcome. And sometimes this will even lead to cases where models will get the right answer, but for the wrong reasons. So why is this important? Especially as we start embedding neural networks into our models. Neural networks are way more overparameterized than your traditional hydrologic models. So if you can kind of see this behavior already in hydrologic models with, let's say, 10 parameters, then as we start adding neural networks with thousands, hundreds of thousands of parameters, uh, there's a very real chance that neural networks will learn to compensate for these solver artifacts instead of actually correcting for the structural problems, which is what we want when we're doing hybrid machine learning. So to address this, we have decided to build a hybrid model where we are paying very close attention to the kind of numerical solvers that we use. And before I get into the hybrid model, I'm going to set the stage for the physics-based backbone of the model that we're using. So the model that we're using is called Land Atmosphere Dynamics model, and it's a model that came out in 2002, which is an improvement on the classic Manabe model, Manabe 1969 model. And they added a bunch of improvements, but the main idea in the model structure is that we have the energy balance side where we're representing our soil layer as a five-layer thing, and each has its own temperature, and we're solving the heat diffusion equation. And on the water balance side, it's a very traditional hydrologic model. It has the snow state, the root zone, and the deeper groundwater zone. And the way they're coupled is there's a snow sublimation that directly relates both latent heat flux and snow melt essentially. And there's also a link between evapotranspiration and latent heat flux, which is pretty obvious. And this is how the two sides of things are coupled in this model. And for our hybrid model, we're using very simple MLP to parameterize our process equations for latent heat and sensible heat flux. And we're implementing the whole model and the MLP in JAX, which is a differentiable solver, which has come up quite a few times by now, I guess. And yeah, so it's a very traditional framework where we solve our hybrid model with a ODE solver. We get our sensible and latent heat flux, calculate our loss function based on the observational data, and then back propagate all the way to our MLP uh, to learn a better process equation. And the data set that we're using is FLUXNET, which has half-hourly observations of sensible and latent heat flux all over the globe. And for this study, we're considering a simplified experimental design where we're testing our model on two sites. One is the Metolius site in Oregon, and the next is the Walnut Gulch site in Arizona. And first experiment that we're doing is we're comparing our MLP parameterized model, a hybrid model, to the baseline physics model that has been calibrated. And the second thing we're investigating is there a reason we need to do hybrid modeling and couple these two tightly? Is there any way in which the internal model states ends up helping our MLP, or is it not needed at all? So the first thing we observe is that our MLP parameterizes latent heat flux better, especially in the diurnal cycle at the bottom. You can kind of see that the hybrid model has kind of reduced this bias at the top. And also in the next site in Arizona, also you can kind of see that hybrid model is doing significantly better than our calibrated physics-based model, which is we expected. And the next more important question I feel like is does our MLP need physics? Because we could also have devised an experiment where we kept MLP external to the physics-based model, but what the results show is that the coupling, especially when we provide model states to the MLP, ends up providing us a better parameterization. Again, you can kind of see this reduction in bias quite a bit, especially with model states being provided. And in the case of latent heat flux, that would be soil moisture, which is very important in calculating latent heat flux. So this is our work so far, and our plan is to scale this up to all the different FLUXNET sites. And before I end, I kind of want to touch on the bigger question of how we should be designing hybrid models, because based on what we're seeing in hydrology so far, I can kind of see two different approaches. One is to learn the parameters of physics-based models, and the next is to learn the actual process equations, which I feel like are two different things. And the main difference I feel like is that when we're learning parameters of physics-based models, we are in some way limited by the structure of the underlying physics-based model, whereas in flux parameterizations, there's an opportunity to learn something different. And once we have trained our MLP, we can do something like a symbolic regression and kind of rediscover what the process equations could be. And there's also some additional design details that I feel like do not really come up in discussions with hybrid models. And first is, how do we spin up a hybrid model that has random neural network weights? I feel like this is something that everyone who works with hybrid models does in one way or another, but it's not really discussed too often. And next is, how do we carry over model states from one sample to the other? And this is especially pertinent for ODE solvers, because if we choose, let's say, an adaptive ODE solver, we are bound by the samples, the sequence length, and it can no longer do the adaptation beyond the sequence length. So how do we do the state handover between samples? And next is, especially when we're working with half-hourly fine resolution data, how do we deal with the vanishing gradient problem, especially when using recurrent neural networks? So I feel like there's some questions that we need to talk about as a community here, Matt. Thanks.
Yeah, thanks for the presentation.